Okay, this is our first example using DNA sequence to do BLAST. Next, let's do another BLAST using protein sequence. Let's go back to the edit search. Choose the blastp program. And let's use a human hemoglobin beta protein to do the search. This sequence is available in my slide. You can copy and paste it into the search section. And by default, the database actually is non-redundant. I show the UniProt because I did previously I did a BLAST. So by default, it's non-redundant protein sequence. And if we do a first step of screening, I just want to determine whether the query sequence has been studied by others before or not, then we can use this database. But even though it's rich in content, but it's not every record has detailed and accurate annotation. So since our goal is to annotate the query sequence as accurately as possible, let's choose the SwissProt database below. It's also called the UniProt SwissProt database because SwissProt database is part of the UniProt protein database. And every record in the SwissProt database has been manually curated by a team of experts. Every sequence contains comprehensive information about the structure, modifications, functions, and comprehensive links to other relative databases. So we often use the SwissProt database as a starting point when we need to annotate new sequences as accurately and as so roughly as possible. Let's limit our search for human first, Homo span. And then for the program selection, we can choose BLASTp or PSI BLAST, that's for multiple sequence alignment, or PHI BLAST and Delta BLAST. If you are interested in those, you can look at the detailed descriptions. And then we can do the BLAST. Okay, here are the results. So first, similar to the DNA sequence BLAST, is to show you a heat map, heat table. So since we confined to just within human sequences, so we can see we find the hemoglobin beta, delta, gamma, and alpha, zeta, theta. That's all the hemoglobin proteins subunits. So it will give us a hint on the functional about the function of this protein. And the E-value is all very small, except the last one. We can also have a graphic view. So not every subject sequences are 100% covered with our query sequence. Some of them just partial covered. And the alignment view. For this alignment view, it has been changed over the time. How to read this? So we can look at some help information. To read this report, you can click this. And there is a very good tutorial, very detailed explanation on how to read the results. And we can just scroll down to the very bottom. So you can see that If we choose the alignment view as a pairwise, then the letters is identical match. And the plus sign here is a positive match. So it's considered as a conservative substitution, means that it's pretty similar, even though these two amino acids are different, but it's very similar, very conservative. And the white space is not a gap. It actually means the 0 or negative score. And the dashes means the gap. And there are also other views you can choose, and you can read this in details. So here, let's look at some example. The plus sign means it's conservative mismatch, and a gap means it's scored 0 or negative, and the dashes means there is a gap. Okay, now we can go back and edit our search. Remove the species limitation. And let's do the BLAST again. This time it will take a little bit more time since we removed the species limitation and it covers all the species. Okay, this time it took about 1 minute to finish the run. Let's look at the result. The first result is very similar. It's almost the same as previous one, but the number of hits obviously is increased significantly. And there are many hits distributed in different species other than human. So that means BLAST did find many possible homologous sequences. In order to view the results more clearly at the species level, we can select the taxonomy report to arrange the hit results by species. Here, the human gets the highest score and is arranged by different species. Also, we can make evolutionary tree. Back to the description. Select the distance tree. Here you can select the different tree method and the different distance. And in the tools, we can change the layout to circular trees. Okay, so we can see that the BLAST indeed can find many possible homologous sequences from different species. And today we have used one example to show the basic process of performing functional and evolutional analysis on database search within and between species using BLAST.